Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 6 of an 8-part series, little mini series within that big playlist. Here we're looking at balanced two-factor factorial design with interaction, and we're going to look at the random effects model. Now the model in previous videos was y equal x star beta star plus epsilon. So it is a linear model. And then we partitioned it into a constant term, the part associated with factor A, factor B, and their interaction. And in previous videos, we assumed these parameters were unknown, fixed unknown parameters. But in this video, we're going to assume that they're random variables. So alpha is normally distributed, mean zero, covariance matrix, sigma alpha squared times I. Similarly for beta, it's going to be normally distributed, mean zero, covariance matrix, sigma beta squared I. Interaction term, remember this is not the product of two numbers, this is a vector. I've seen it where they just call it gamma, but alpha beta and then with parentheses it sort of emphasizes that it's the interaction space. So it's normally distributed. The error term of course is normally distributed, mean zero, constant variance. All these parameters are all independent. So let's derive the mean of our model. So if we look at the expected value of y, and then it goes into each of these terms, but each of these parameters have a mean of 0, so they go away, and it's just equal to that constant vector, mu times the 1 vector. The variance, since all the terms are independent, there's no covariance associated with them, so it's just the sum of the variances of each of these. Wait, where did the constant term go? Remember, if you take the variance of a constant, it's 0, so it just drops out. Now here, so the variance you take it out this way, and then you take it out back transpose, and then it's just the variance of the alpha vector, which is sigma alpha squared times I. So the I kind of goes away in this matrix product. In the same way here, you bring it out front. And I have a video called Random Vectors and Random Matrices if you want to see much more detail about how to take the mean and variance of random vectors and matrices. So this comes out front and it's transposed out back times the variance of beta, which is sigma beta squared times I, so we get this. Similar approaches here. Now, the perpendicular projection matrices associated with this, if we were to just divide this by b times n, it becomes a perpendicular projection matrix onto that space. But if you divide, you have to multiply. So we're multiplying this by 1. And then this is going to help us in a bit, having this perpendicular projection matrix here instead of this matrix product. And we can do something similar for here. We multiply by 1 by a times n over an, but the denominator goes into this and creates the perpendicular projection matrix on a column space of the beta. And the same way for sigma alpha beta squared, we can multiply it times 1, n divided by n, and then we can get that perpendicular projection matrix. And sigma squared I, we just leave it as is. Now, as a reminder, this has a specific form. It's block diagonal with a matrix of all ones. So normally it would be divided by Bn, but then that comes in and we get, it makes it all ones. And I'm gonna have to point you to parts 1, 2, and 3 for more detail. And then, and I'm showing you this because when we do the covariance, it's going to make sense. So this is block diagonal of all ones. So think of a big matrix, A times B times N by ABN. So it's big and it's a block diagonal of all ones. And here it's a block diagonal. So block means the whole matrix is formed of blocks, but each block is block diagonal. And then this one is block diagonal U, and then of course sigma squared I just comes down. Now, in order to understand that, you have to go through that monotony of deriving this. Write it out, derive these, write it out, figure it out. And then it's going to make what this section much easier. So let's look at the covariance between any two components of this vector, right? That's what we're doing. So this has created a covariance matrix. And so we want to find the covariance between any two components of this y vector, which lives in this matrix, right? And the rule of thumb is if I is equal to I prime, then we're going to add a sigma alpha squared, which means we get one of those. And then if we add if a j and a j prime are equal, then we add a beta, which deals with this part of the matrix. Here is if I equal I prime and j equal j prime, then we add a sigma alpha beta squared, which is what this deals with. Now if they all equal, so I equals I prime, j equals j prime, and k equals k prime, so it's ijk, ijk. So we're really dealing with the diagonal, a diagonal element. So we have to add a sigma to it. And so some quick examples, if we have the covariance between y213 and 223, then that's just sigma alpha squared, right? Because the i's are equal, nothing else is. The third component is, but in order to add a sigma, they all have to be equal. So 213, 113, the ones are the same, so we're going to add an sigma beta squared. The covariance between 213 and 212, since the I components and the j components are equal, we add a sigma alpha squared, a sigma beta squared, and then we have to add in a sigma alpha beta squared. And then of course if the terms are the same, we're looking at the covariance, so we add each component. Now the expected sums of squares, so if we take the mean of this, so this is the sum of squares for factor A, the formula, and I have a video called the mean, the variance, covariance of quadratic forms, which is very informative, and we derived this proof, the theorem that we're using. It says take the trace of that matrix times the variance of y, and then it's plus the mean of y times this matrix times the mean of y, and don't forget the transpose in there. Now here we're bringing it down, so we have m alpha minus j, and times this variance, which we said was this, we derived up here. The mean of y we said was mu times the 1 vector, and everything comes down. Now one note here is this is the perpendicular projection matrix on the orthogonal complement space of 1 with respect to x, to m alpha. And this is 1. So this times this is going to be 0. So that drops out. And then over here, if we take this matrix times this, we just get m alpha minus j back. This actually drops out to 0 because m beta times alpha, m alpha, is j, and j times m beta is j, so you get j minus j. So this is 0. This, we just get this back, and then that times I, you just get it. So then we'll write that on the next page, and then that's what we get. So it's, remember, so don't forget about the trace, right? The trace out front. So then the trace of this addition is the addition of the traces. So that's why we can separate it into the difference. But then the trace of these projection matrices, they're idempotent, so it's the rank. So that's the trace. It's not a plus R, that's the trace. So this is A minus 1, which is what this is. This is A minus 1, and that's A minus 1. So now this is the expected value of the sum of squares for treatment A. Now if we divide by A minus 1 and then take the expected value, then we just get what's left over. And this is going to play a part when we develop f-tests. Now similarly for the mean square for treatment B, we can go through that same exercise and get an times sigma squared, sigma beta squared plus n sigma alpha beta squared plus sigma squared. Now the expected value of the sum squares for interaction, so this is the quadratic form for that, then it becomes the trace of this matrix times the variance plus the mean of y, transpose times that matrix, mean of y. Well, this is going to drop out to 0 again because this is the one vector, and this is a perpendicular projection matrix that projects orthogonally onto that one vector. So this is going to be 0. So we're left with this. So this comes down, and the variance was this. Now, here, this matrix times m alpha is going to be 0 because this is projecting orthogonally onto that space, so that it's 0. Same here. This is 0, right? It's projecting orthogonally. This is, we're going to get this back, so that's why this comes down, and then that times I, we just get it. So it's sigma squared times this matrix. Now, don't forget about the trace. And then, so the trace of these matrices is A minus 1 times B minus 1. And we derive that in part 2. A minus 1 times B minus 1, sigma squared. And then we get, N sigma squared out here. So if we were to divide this by A minus 1 times B minus 1, and then take its expected value, those constants are going to drop out, right? Because we're dividing by. And we get N sigma alpha beta squared, and then we just get sigma squared. Now, all right, we'll do one more, and I'm telling you why this is so important to go through this exercise, this monotony of calculating these. Because when you're in the random effects model, it's not, the f-tests end up not being what you think they should be. So the expected value sum squared error, this is the error. So it's the trace of that matrix times the variance, this matrix times y. This is 0 because it's I minus m times the one vector is going to be 0. The variance comes down. These are all going to be 0, right? Because it's projecting orthogonally onto, from that. So this is 0, it's projecting orthogonally onto that. So that's 0, and here we just get it back, right? So then the trace of I minus m is AB times n minus 1 sigma squared. So if we divide the sum of squares by this quantity, so the expected value of the mean squared error, which is sum of squares divided by its degrees of freedom, then this ends up just being an unbiased estimate of sigma squared. But in the next video, when we look at the f-test, we're going to divide by the mean squared for the interaction term, not the mean squared error, right? And so under like a null hypothesis, we'd assume that alpha is sigma alpha squared is 0. So why is that important? So look at this term here. So the mean squared for the interaction term, and that's what I'm saying we're going to divide by, is this. So then we look at the mean squared, say for treatment A, which is this. So under the null hypothesis, if sigma alpha squared is 0, then what's left over is this, which is the same as that, so it's going to be 1. It's going to be, it's not going to be in the rejection region. But if we divide this by the mean squared error, which is sigma, and sigma under the null, sigma alpha squared is 0, we're still left with this, which could be pretty significant, could be big. So it could, even though the null hypothesis could be true, we could still be in that rejection region and falsely reject. Anyway, but more on that when we look at the next video. Hopefully you enjoyed this. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.